In a previous lesson, we talked about the vector equation of a line in relation to other forms of a line, particularly the slope-intercept form and the point-slope form. This time, let's look at the vector equation of a line from a vector addition angle. So let's say that this point represents a particle that is moving at a constant speed, and its direction vector is a vector b. Suppose a sub 0 is its original location, and let's say that after 1 minute it is here at a sub 1. If we let this vector r, which is the position vector of the new location of the object after moving for 1 minute, if we let that vector as vector r, notice that it is actually the sum of the position vector of its original location, which we are going to call a, and the direction vector b after 1 minute. So after 1 minute, so I'm going to call this r1. r1 is equal to a plus b. Now let's say that after 2 minutes the vector is here. We'll call its new location as a2, and the position vector of that new location, of that point representing the new location, if we call this position vector as r2, notice that that is actually the sum of the position vector of the original location plus this vector, which is actually 2b. So we could say that r2 is equal to a plus 2b. And if the pattern continues, the linear path of the object is formed, and the equation of that line is represented by r is equal to a plus tb, where t represents the time in minutes. And as we said before, this equation is called the vector equation of a line. I'm going to write it here. It's the vector equation of a line, and b is the direction vector, while a is the position vector. In general, a is the position vector of any point on the line. I'll write it as. So now let's take this example. Suppose a line L passes through the point 1, 5, and its direction vector is the vector 3, 2. How do we write the vector equation of the line? The vector equation of line L. Well, we are going to use r is equal to a plus tb, and this is going to be direct to the point because we are already given the point. And so since a is the direction vector of any point on the line, our a here will be the position vector of 1, 5 from the origin, so that's just 1, 5. plus t, the direction vector is already given. So it's 3, 2. And again, remember that because r is a vector, it has an x component and a y component. So we could write it. We could write this equation as xy equals 1, 5 plus t, 3, 2. And from here, actually, we could break this equation into two equations, one in x and one in y, because if the left-hand side is, since the left-hand side is equal to the right-hand side, we could equate the exponents and say that x is equal to 1 plus 3t and y is equal to 5 plus 2t. And this format is actually helpful, like in the example a while ago, in the moving particle example that we did a while ago. One possible problem that you might be able to answer using the vector equation of a line is to determine the location of the point after a given time. And what will help you in answering that question is the x and the y coordinate of the point representing its new location at that particular time, in which case this format is, and this format has a special name. It's called the parametric equations of line L. And remember that t here is a scalar, and in our moving object example a while ago, t represented time. So if t is a scalar, so it means that t could be any real number. And like I said in our previous example, this represented time, and it has a special name. T element of R, or t could be any real number, and it has a special name, is called the parameter in this case. And this is why these xy equations are called the parametric equations of the line L. Another question that might arise in such situations as the moving particle example that we did a while ago is when you want to know the time in which the particle is at a particular location. So if you look at the each of the parametric equations, x and y on top, we could actually express each of them in terms of t. So in the x equation, for example, we could write that equation as 3t is equal to x minus 1, and y is equal to, 2t is equal to 5 minus y. So t here is equal to x minus 1 over 3, and t here is 5 minus y over 2. And combining the two equations, we could combine the two equations as t is equal to x minus 1 over 3 equals 5 minus y over 2. And this new format is called the Cartesian form. Cartesian equation of L. And this is convenient to use when you're looking for t.